Okay, it's recording. Okay, so you have that bounded region and you rotate it around the y-axis. So you're rotating this around the y-axis, right? And now you have this rotated three-dimensional region. I'm going to also rotate the point on the x-axis and rotate this point on the x-axis. Okay, so you're taking that bounded region, blue, and you're rotating it around. So we're using the method of cylindrical shells. So to do that, I'm going to draw an example of a cylindrical shell. So let's say you have that vertical rectangle and you rotate it around, then you get this cylindrical shell, which it makes up part of the entire object. Let me just show that one better here. So, that. Okay. So now we have this cylindrical shell, and so to find the volume, we're just going to calculate the integral corresponding to these choices of cylindrical shells. So V is going to equal to V is equal to doesn't equal sign doesn't have to be perfect. V is equal to the definite integral from 1 to 2, because it's going from x equals 1 to x equals 2 on the x-axis here. These x values are ranging from x equals 1 to x equals 2 in the blue region. That's why it's 1 to 2 here. This is a equals 1, b equals 2. Okay, then the formula for cylindrical shells is 2 pi, and now r is the x coordinate, because the radius of the cylindrical shell is how far away, right? If you look at the radius of each of these circles that make up the cylindrical shell, the radius is the x coordinate of the point you have on the curve y equals x cubed. So x is the radius, so it's 2 pi x times the height. Now the height of each cylindrical shell that you're using is the height of the graph y equals x cubed. So it's 2 pi r h dx. And so when you calculate this definite integral, you find the volume of that rotated region. And so when you calculate this, you get 2 pi times the definite integral from 1 to 2 of x to the 4th dx. And so this is equal to 2 pi times x to the 5th over 5. Evaluate from 1 to 2. And so that's equal to 2 pi times 2 to the 5th is 32. I'm going to factor out the 1/5. And so then it's 2 to the 5th minus 1 to the 5th. That's 32 minus 1, which is 31. And so that's your answer. So the answer is 62 pi over 5. So this is equal to 62 pi over 5. Okay, did that explain it? Okay, so this is number 4 in 7.3 homework. Okay, so that's the solution. Okay, so I'm going to go back to Word. Okay. So the solution is on the whiteboard. Okay. Any other questions with the homework? Okay, let's go. So now let's continue with the material. So we were up to 7.7, which is on differential equations. Okay, so definition. A differential equation is an equation that contains an unknown function and one or more of its derivatives. Okay, here are some examples. This is the definition of a differential equation. Underline it. Okay. Differential equation is an equation that contains an unknown function and one or more of its derivatives. So here are some examples. The first example is y prime is equal to xy. So this is an equation that contains an unknown function y and its derivative y prime. So this equation contains the unknown function y and one of its derivatives y prime. Okay, and so that's why it is a differential equation. Okay, the second one is y double prime plus 2y prime plus y equals 0. And so this equation also contains the unknown function y and two of its derivatives, y double prime and y prime. Right, and by two of its derivatives, I don't mean the coefficients. It has to do with coefficients. I mean that the functions y double prime and y prime are in the equation. This y prime and that y double prime. Those are its derivatives. Its first derivative and its second derivative. Okay, and then another equation. If you have d3y dx3 plus x times d2y dx2 plus dy dx minus 2y is equal to e to the negative x. This is also a differential equation. Okay, contains an unknown function y and one or more of its derivatives. Specifically, it contains three: the first derivative, second derivative, and third derivative. The only difference here is this equation uses Leibniz notation for the derivative. You could use y prime. You could use y prime, y double prime, y triple prime instead, and it would say the same thing. Okay, so there's nothing special about the fact that this equation is using fractions and these are just using primes. They're just two different notations describing the same equation. Okay. Okay, so in these equations, in these differential equations above, y is an unknown function of x. Okay, so frequently equations done in applications involve differential equations. Okay, and so it's very important to be able to solve differential equations. Okay, so another definition. The order of a differential equation is the order of the highest derivative that occurs in the equation. Okay, so that is the definition of the order of a differential equation. Okay, so thus the equations 1, 2, 3 above, these ones 1, 2, 3, have as orders 1, 2, 3 respectively. It's the order of the first equation is 1 because the highest derivative is the first derivative. The second equation is order 2 because the highest derivative is the second derivative. And the third equation has order 3 because the third equation has highest order derivative 3. All right? That's the definition of the order of a differential equation. Another definition. A function f is called a solution to a differential of a differential equation if the equation is satisfied when y equals f of x. Satisfied means solved, okay? So satisfied slash solved when y equals f of x and its derivatives are substituted into the equation. Okay, so that's the definition of a solution of a differential equation. Okay, so a function f is called a solution of a differential equation if the equation is satisfied or solved when y equals f of x and its derivatives are substituted into the equation. Okay, thus f is a solution of equation 1, which I'll remind you is y prime equals xy from above. So thus f is a solution of equation 1, y prime equals xy, if f prime of x is equal to x times f of x. Okay? So our unknown function is y equals f of x. And so our unknown function is y, right? F is a solution of that equation if you can substitute the function f and its derivatives into this differential and it's true. Okay? So that would mean this equation saying that f prime of x would have to equal x times f of x. Okay? And so if that happens, then f is a solution of that equation. Okay? And I should mention for some values of x. So for some values x in some interval. Okay? So we're talking about this function f somewhere on the real line, right? So what you want is this equation not just to hold for maybe a particular value of x, but on the entire domain of f, right? So for every x in the domain of f, it should satisfy the differential equation in order to be a solution. Okay. Okay. So when we are asked, this is a note. Okay. When we are asked to solve a differential equation, we are expected to find not just one solution, not just one function that satisfies the differential equation, but we are expected to find all possible solutions of the equation. Okay? And these solutions are not numbers, they're functions. Okay, so when we're asked to solve a differential equation, we're expected to find all possible functions that you can plug into the differential equation and have it hold true. Okay. Okay, and once I have to get something real fast for you. Okay, I'm back. The notes continue on another book. Okay. Okay. So this must be this. Oh, okay, found it. Okay, good. Okay, I put it in a separate spot. Okay, so continuing. So that's the definition of differential equations. And so now specifically, you can classify differential equations as different types. So one type of differential equation is a separable differential equation. So let me define a separable differential equation. A separable differential equation is a first order differential equation that can be written in the form dy dx is equal to g of x times f of y. Okay, so this is called a separable differential equation. Okay, so if you can write your differential equation in the form the derivative of y is equal to g of x times f of y, then you have a separable differential equation. Okay. Equivalently, if what's going on? Okay. Oh, good. Get rid of it. Okay. Equivalently, if f of y does not equal 0, we could write that dy dx is equal to g of x divided by h of y. Right? So we would like to say that dy dx is equal to a fraction, right? G of x over h of y, where h of y is equal to 1 over f of y. Okay, so if you're dividing by h of y, and h of y is 1 over f of y, dividing by h of y is the same as multiplying by f of y. Okay, you can only do this if f of y does not equal 0. If f of y does not equal 0, then you can define a function h of y to be 1 over non-zero values. Okay, but if f of y does equal 0 anywhere, then that means you cannot define this function. You cannot consider this function because the denominator would be 0. Okay, so to solve this equation, we rewrite it in differential form. Okay, so in differential form, this is saying that h of y dy is equal to g of x dx. And so the way to see that is just cross multiply, right? H of y dy equals g of x dx. Okay, so it's not the reason they're equal. It's just a helpful memory technique to remember this, right? So dy dx equals g of x over h of y, and then h of y dy equals g of x dx as differentials. Okay, this has to do with the change in height of the tangent line at a point. Okay, so okay, and this is so that all the y's are on one side of the equation, and all the x's are on the other side of the equation. Okay. So now once you have that those two differentials are the same from here with that assumption, you can then integrate both sides. And when you integrate both sides, you get that the integral of h of y dy is equal to the integral of g of x dx. Okay, and so in the book, this is labeled as equation 5 in this section. Okay, so equation 5 defines y implicitly as a function, of x. Okay, explicitly would be, let's say, y equals x squared, right? Implicitly it would be like 3y plus 7 equals x squared minus 4, right? Okay, so reminder, right? An equation like y equals x cubed would be this lower y equals x cubed would be solving for y explicitly in terms of x, right? And then if you had the equation y squared plus 7y minus 5 is equal to x cubed plus 4, this would be solving for y implicitly in terms of x, okay? So sometimes when you want to solve for y, you just get that it's a solution of an equation instead of getting explicitly what it is. And that's fine, but sometimes that can be fine. That would be solving for y implicitly in terms of x in this example, okay? So equation 5 defines y implicitly as a function of x. So these are, right, these are just examples. It's not that they have different equations, right? Examples illustrating defining a function implicitly in terms of x, okay? Okay, so in case you're getting confused by this implicitly thing. Okay. Okay, and this means that y is a solution. Y is a solution of this equation. Okay. Okay, so solving a differential equation. Yeah.
Can you explain the explicitly and implicitly thing real quick?
Right. So y equals x cubed, right? That's solving for y explicitly. Does that make sense?
Yeah.
Y squared plus 7y minus 5 equals x cubed plus 4 is solving for y implicitly in terms of x, because instead of saying y equals saying y is something, here you're saying you're solving for y by saying it's a solution of this equation. Does that make sense?
Okay. Yeah. Thank you.
Yeah. Okay. So here, what we're saying is that here equation 5 defines y implicitly as a function of x, because you're not saying y equals something. You're saying y is a solution, solves this equation. Does that make sense? Where it involves integrals. Okay. So given this equation, if you can find y from this equation, you would be finding y explicitly. If you don't find y specifically, but you know it's a solution of this equation, you've now solved for y implicitly. Okay, so solving a differential equation means finding all possible solutions to it, right? Which are functions. Usually though, we are not interested in finding all solutions, but instead finding a particular solution to the differential equation that satisfies some condition or conditions. Okay, so if you have a general differential equation, if you have a differential equation, then you could possibly have infinitely many solutions, infinitely many equations that solve, infinitely many functions that solve that differential equation that you can express in some algebraic form to represent all the infinitely many solutions of that differential equation. But what's usually, what people usually want when studying differential equations is you have your general differential equation and you have a condition on it. And then oftentimes the goal is to find the one solution to that differential equation, the only one that satisfies the condition you put in addition to that differential equation. Okay? And so this is called the condition is called an initial condition. And the problem of finding a solution of the differential equation that satisfies that initial condition is called an initial value problem. Okay, so here I'm defining an initial condition and an initial value problem. Okay. I don't want to say, I'm just going to leave it like that. Okay. So now let's do an example. So example 1. So for part A, solve the differential equation dy dx is equal to x squared over y squared. Okay. B, find the solution of this equation that satisfies the initial condition y of 0 is equal to 2. Okay, so we have both finding all the solutions of a differential equation in A, and in B we have solving an initial value problem. Okay, so solutions. So part A, so we write the equation in terms of its differentials and integrate both sides. Okay. So to write this in terms of its differentials, you have y squared dy is equal to x squared dx. That would be writing it in terms of its differentials, right? And then you're going to integrate both sides. And so it's the same equation, just with the integral sign in front. So you have the integral of y squared dy is equal to the integral of x squared dx. Okay, now that you've integrated both sides, calculate the integral of both sides. You have y cubed over 3 is equal to x cubed over 3 plus the integration constant c. Okay, so now you have this. Okay, and then now, so you've now solved for y implicitly in terms of x, and so this is where capital C is an arbitrary constant. Right, the arbitrary constant you get when you calculate an improper integral. Okay, and so this is solving. So we just solved for y implicitly in terms of x. Now let's solve for y explicitly in terms of x. Okay, and so if you solve for y explicitly in terms of x, you have y cubed. You multiply both sides by 3, so you get y cubed equals x cubed plus 3c. But 3c is just multiplying a constant by 3, and you get another constant. And so in mathematicians call it abusing notation. I'm just going to keep calling this plus c, even though I keep multiplying it by things, because c was an arbitrary constant. And so the idea of what the equation is saying is that the original equation is saying y cubed over 3 equals x cubed over 3 plus any constant you want. So if you multiply both sides by 3, you're still saying y cubed equals x cubed plus any constant you want. If you were to say 3 times any constant you want, that's the same thing as saying plus any constant you want. Okay, so y cubed equals x cubed plus c. So y is equal to the cubed root of both sides. And so if you take the cubed root of both sides, you then have x cubed plus c. Okay, so y is equal to cubed root of x cubed plus c. Okay, and now we have y. Okay. Okay, so for B, find a solution of this equation that satisfies the initial condition y of 0 equals 2. Okay, so just plug in 0 for x. So you have y of 0 is equal to cubed root of 0 cubed plus c. And so that's equal to the cubed root of c. Okay, and so if y of 0 is the cubed root of c, well, we're given y of 0 is 2, right? So 2 is equal to y of 0. Okay, so we're given that 2 equals y of 0, and so y of 0 is the cubed root of c, and so that implies that c is equal to 2 cubed, which is 8. Okay, so if 2 is equal to cubed root of c, that implies that c equals 8. And so now the particular solution, our solution of our initial value problem, is y is equal to the cubed root of x cubed plus 8. Okay, and that's good. And so this is the solution, the only solution of the initial value problem, and the general solution solved explicitly in terms of x for y is this. So these are this is an expression of the infinitely many functions that satisfy this differential equation. Where is it? You have this differential equation, right? And so all the functions y equals f of x you can plug in that satisfies it is our solutions. And so you don't get one solution, you get infinitely many, and they're of this form. And how does this express infinitely many functions as one equation? Well, c is given as an arbitrary constant. And so any constant you plug in for capital C represents its own function that satisfies the differential equation. And you have infinitely many choices for the arbitrary constant c. Each of those infinitely many choices is its own unique function that satisfies the differential equation. Okay? And so all the functions of this form, it represents infinitely many functions, all of which satisfy the differential equation. They're also the only functions that satisfy the differential equation. There's no function not of this form that satisfies the differential equation. So this includes all of them, every single one. Okay, so that's example 1. This is example 2. So example 2 is solve the differential equation dy dx is equal to 6x squared divided by 2y plus cosine y. Okay. Solution. Okay, so writing the equation in differential form and integrating both sides, we have, so I like to have sometimes have, especially when teaching, have a uniform way of saying the beginning of a solution, right? So I started out example 1, writing the same sentence, writing the equation in differential form and integrating both sides we have. And so I wrote the same thing at the beginning of the last solution. I'm writing the same exact thing here. So first, 2y plus cosine y, 2y plus cosine y dy is equal to 6x squared dx. Okay, so this is writing it in differential form. That's the first step. You can think of it as a memory technique, cross multiplying two fractions, right, that are equal. That's not the reason they're equal, but it's just a way to remember it. Okay, so then you integrate both sides. So you have the integral of 2y plus cosine y plus cosine y dy, and that's equal to the integral of the right side, which is 6x squared dx. Okay, and now you just calculate the integrals on both sides. To get y squared plus sine y is equal to x cubed over 3 times 6, that's 2x cubed, plus your integration constant c, right? Now I'll remind you where capital C is an arbitrary constant. Okay, and so we have solved for y implicitly in terms of x. Okay, with that equation, with the equation just above. Okay, this one just above right there. Okay, okay, so we have that. Okay, so it is impossible to solve this equation. It is impossible to solve this express y explicitly as a function of x. Okay, so it's impossible to do that, and so since it's impossible, we have to solve for y here implicitly in terms of x. Okay, and so it's not. So right, you either can solve for it explicitly in terms of x, or you can't. If you can't, it doesn't mean you haven't gotten anywhere, right? If you have this equation, there's ways you can approximate the value of y, right? Maybe you can approximate the function. And so solving for a function implicitly when you can't solve for it explicitly does tell you something about the function, even though it doesn't give a direct equation. And so there are uses for solving a function explicitly in terms of x, implicitly in terms of x. It may just require more math to make that useful. Okay, so solve the equation y prime is equal to x squared y. Okay, so the solution. So remember, solving a differential equation means finding all possible function solutions of it. Okay, so first we rewrite the equation using Leibniz notation. Okay, Leibniz notation is just expressing the derivatives as fractions. So dy dx equals x squared y is an equation that says the exact same thing as y prime equals x squared y, but the notation hints at what we should do next. Okay, so first I rewrote the equation, then we rewrite, then we can write it in differential notation and integrate. Okay, so the fact that we've written in Leibniz notation first tells us basically what the differential form of that equation, of the original equation is. It's y dy dx equals x squared dy. See, it's the cross multiplication where this is over 1. Oh, wait.
And wouldn't it be dy over y?
Yeah, hold on. I'm just fixing it. Dy dx. Yeah, it's dy over y. Okay. Okay, so dy over y is equal to x squared dx. Good. Okay, so so then when you integrate both sides, I'll write in the integration. So you have the integral dy over y. That's not good. Okay, equals integral of x squared dx. And so then you integrate both sides, and then ln of y, ln of the absolute value of y. I don't want a capital word. Ln of the absolute value of equals x cubed over 3 plus c. Okay, so you integrate both sides. So you get ln of the absolute value of y equals x cubed over 3 plus c. And so then now you solve for y. So so the absolute value of y is equal to e raised to this. Okay. So since you integrate both sides, you get ln of the absolute value of y, which is this integral, is equal to this antiderivative plus this integration constant. Now, if you solve for the absolute value of y, you get e raised to this. Okay.
Wait, Professor.
Yeah.
Wouldn't it just be y? Because e can't be negative, right?
Sorry?
This exponential equation can't be negative, right?
Right, but don't forget, we're saying the absolute value of y is something that can't be negative, which means that the absolute y also can't be negative, right? So y could be negative, and its absolute value has to be positive.
Oh, okay. So you leave it like that.
Make sense?
Yeah, it makes sense.
Okay, good. Okay, and then let's note the fact that y does not equal 0. Okay, so y does not equal 0 here. Okay. So Okay, so we have e equals x, e to the x cubed over 3 plus c. Now I'm just going to factor out this e to the c here. So you have e to the c, and then you're multiplying it by e to the x cubed over 3. Right? So instead of adding two things in the exponent, we're multiplying two things with base e and then those two exponents there. Okay, so our conclusion is that y is equal to plus or minus this expression, right? So it's plus or minus e to the c, e to the x cubed over 3. Okay. So now, since the absolute value of y is this, y itself is plus or minus that. Okay. Okay, so before I assumed that y as a function was not equal to 0. Now you can also show, you can also verify that y equals 0 is a solution of the differential equation. Okay, and so because the differential equation we're looking at is this guy, so if dy dx, if y equals 0, then wait, this is not. No, this is the example. Okay, so this is our differential equation. So it's a solution of the difference of this differential equation. That's because if y equals 0 is a constant, its derivative is 0. And if you plug in oh wait, no, this is not. Wait, what just happened here? It's sorry. Okay, so then that's that. Okay, so we have this equation here. So we have that there, right? So you can see if y is 0, its derivative is 0, and the left and right side are both 0. So you can verify that y equals 0 is a solution of the differential equation since both sides become 0. Okay, its derivative is 0, and 0 times anything is 0. All right. So I'm going to call this the final conclusion. We can write the general solution in the form y is equal to a times e to the x cubed over 3, where capital A is an arbitrary constant. Okay, so either A is equal to e to the c, or A is equal to negative e to the c from earlier, or A is equal to 0 from the y equals 0 case. Okay. Okay, so if you have y is of this form, or y equals 0, you can write this e to the c as capital A, where capital A is e to the c, or negative e to the c, or if the solution y equals 0 you want to consider, then you let A equal to 0. Okay, and since e to the c is any positive value, if you can choose any c you want, e to the c is any positive value. You can choose any c you want. Negative e to the c is any negative value, or a equals 0. So this a can be any arbitrary constant, where a is an arbitrary constant, right? Because all the real numbers are exhausted by a's of this form, a's of this form, and a equals 0. These three exhaust all possible choices. Once they all can be chosen, and they all exhaust all the real numbers. And so you could just write where a is an arbitrary constant. You don't even need this part, but I'm just illustrating how you reach this conclusion from what I wrote up here. Okay. So that's example 3. So next is example 4. Okay. Solve the equation dy dt is equal to ky. Okay. Solve dy dt equals ky. Solution. Okay. So this was called the law of natural growth. Okay. In section 5.5. Okay. So we can solve it here using these new methods just discussed. Okay. So we write this equation in differential form and then integrate both sides. Okay. So we write this equation in differential form and we integrate both sides. And so when we write it in differential form, we get dy is equal to ky dt, black. We get dy over y is equal to k dt. Okay. So this is writing it in differential form because it's 1 over y dy, which I'm writing dy over y for. So dy over y is equal to k dt. That's in differential form. Then we integrate both sides, and then we calculate the integral on both sides. So we have the integral of dy over y. Dy over y is equal to the integral of k dt. Okay, so we have those two integrals are the same. Then we calculate both those integrals and set them equal to each other. So you have ln of the absolute value of y, ln of the absolute value, ln of the absolute value of y is equal to kt plus c. Okay, and so then we exponentiate both sides and we get the absolute value of y is equal to e raised to the right side, so kt plus c. And this is equal to e to the c times e to the kt plus e to the kt. Okay. And so we have the absolute value of y is equal to that. And so since y is absolute value of y is equal to that, that means that y is equal to plus or minus e to the capital C, e to the kt, right? And y equals 0 is also solution. So y equals that, or y equals 0. Okay, that's just from knowing that y equals 0 solves that differential equation. And so, so we can express the conclusion.
Excuse me, Professor.
Yeah.
How does y equals 0 solve the differential equation?
Okay, so we have this equation here, dy dt equals ky. So, okay, so y equals 0 solves the differential equation since it makes both sides 0, right? If the equation is y equals 0, it's a function that always takes the value of 0. So what is its derivative with respect to a variable t?
0 as well.
It's 0, right? Well, so it's 0, right? So y equals 0 is a function of t. As a function of t, its derivative dy dt equals 0, right? And then k times y, what's that?
0 when y is 0.
Right. So then you see how both sides are the same?
Yeah.
And so y equals 0 is a function where for any value of t, the output is 0. So y is a function of t. So y equals 0 is saying y is a function of t is 0. So y of t equals 0 solves that differential equation since it makes both sides 0 for any t, for every t. For every t. Okay? So the conclusion is that since we have all solutions either of this form or this form, the conclusion we can make is that we can express all of the solutions of the differential equation in the problem we can express all of the solutions of the differential equation in the problem as being of the form instead of as being of the form, right, as being y is equal to capital A e to the kt, where capital A is an arbitrary constant. Okay, you can express A as being e to the c for any value c, or negative e to the c for any value c, or 0. But those three exhaust just all real values. Okay, so the final answer is that you can express all of the solutions of that differential equation from the equation y equals capital A e to the kt, where capital A is an arbitrary, and I'm going to put here real because that's what I mean, arbitrary real constant. A is a real number. Okay? So that's the solution to example 4. Okay, and so that's the end of 7.7. Okay, and so now we're going to move on to 8.8. Okay, so this is the end of 7.7 and the end of what we're covering in chapter 7 in this class, and it's the end of the material on test 2. Okay, so at this point we've now covered all the material for the second exam. Okay, and so remember the second exam is on April 26th, right, during class. Okay, April 26th at 1:40 p.m. Okay. Okay, so reminder, test 2 is on April 26th at the start of class, 1:40 p.m. Okay, test 2 is on April 26th. Reminder, April 26th at the test 2 is on April 26th at the start of class at 1:40 p.m. Okay, and remember, another reminder, the review sheet has been there for a while. The review sheet is online on Blackboard, right? So you just go to tests on the menu bar link, then go to test 2. The review sheet is there. Okay, so we finished chapter 7, and so next is chapter 8. So chapter 8. Okay, so chapter 8 is on series. Okay, and so 8.1, the topic is sequences. And so we're going to first talk about sequences, and then once we know enough about sequences, we can define what a series is, and then we can do mathematics about series. Okay, so first the definition. So we're talking about sequences first. That way we can later define what a series is. Okay, so definition. A sequence can be thought of as a list of numbers written in a definite order. Okay, so for instance, this is one example of a sequence using notation. So A1, A2, A3, A4, A5, and so forth. And then you get to the nth term, so you have AN, and then you keep going, right? So A1 here, A1 is the first term, A2 is the second term, and then you keep going, dot, dot, dot. an is the nth term. Okay, and then dot dot dot, because there's then an n+1 term, an n+2 term, and so forth. Keeps going, goes on and on. Okay. And so this is the definition of a sequence. A sequence can be thought of as a list of numbers written in a definite order. You can have a sequence of things other than numbers, but here in this, the way we're using it is we're going to think of a sequence as a list of numbers written in a definite order. Okay. As an example of a sequence, just you could take this as a sequence, the sequence n from n equals 1, from k equals 1 to infinity. Okay, this is just the sequence of numbers where the nth term is defined, the kth term is defined by n. So the first term, k equals 1 term is 1, the k equals 2 term is 2, the k equals 3 term is 3, and so forth. Okay, actually, sorry, n equals 1 to infinity. And then that's the sequence. So the first term is 1, the second term is 2, the third term is 3, and so forth. This is an example of a sequence. It's a list of numbers written in a definite order. The first one is 1, the second one is 2, the third one is 3, and so forth. They don't have to be increasing. They don't have to have any particular pattern. You just define what your list is, and then that list is a sequence. Okay? Okay, so we will deal with infinite sequences, and so each term, a sub n, has a successor, a sub n plus 1, which is the next. Okay, so the nth term is a sub n, but since it's an infinite sequence, that means there's always going to be a next term, a sub n plus 1. Okay, it's like walking up a staircase that has infinite steps. Whatever step you're on, there's always going to be another step. So wherever place you are in the sequence, there's always another term. There's always a next term you can look at. Just like there's a next step in an infinite staircase. Okay, so for every n in the set of positive integers, okay, so z represents the integers, and z sub plus represents positive integers. Okay, so notation. Okay, z represents the set of integers. Okay, z sub plus is the set of positive integers. Okay, so that set is the set 1, 2, 3, 4, 5, 6, 7, 8, and so forth. That's the set of positive integers. Set of integers, right, is the set 0, 1, -1, 2, -2, 3, -3, 4, -4, and so forth, right? So I wrote it that way, alternating. That way I can cover all integers with how I'm representing them. So 0, 1, -1, 2, -2, 3, -3, 4, -4, and so forth. That's the set of integers. That's the set of positive integers. Okay, so for every n, epsilon means in the set, right? But I guess I'll just use the word in. Okay, so for every n in z plus, so for every n in the set of positive integers, there is a corresponding number, a sub n, and so a sequence can be defined as a function, put it like this, as a function f from the set of positive integers to a, where capital A is any set. Okay. But we write A sub n instead of f of n for the value of f at n. Okay, let me just, okay, that's notation, right? Okay, so so for every positive integer n, there is a corresponding number a sub n. And so a sequence can be defined as a function f from the positive integers to capital A, where A is any set. Okay, but we write a sub n instead of f of n for the value of f at n. So let me illustrate with this an example. So example illustrating this, illustrating the above, illustrating the just above. Okay, so let's say you have a sequence. Let's say you have a sequence. Let's say you have the sequence n squared. Okay, from n equals 1 to infinity. I'm using the notation right for a sequence, and so you're seeing me do this in examples. So okay, so this sequence would be 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16, 5 squared, which is 25, 6 squared, which is 36, 7 squared, which is 49, 8 squared, which is 64, 9 squared, which is 81, 10 squared, which is 100, and so forth, right? And 11 squared is 121, and it keeps going. Okay, so this would be the sequence of n squares from n equals 1 to infinity, right? So if you want to know the first term, right, the first term is 1, the second term is 4, the third term is 9, the fourth term is 16, and so forth. This is a list, right? This is a sequence. So this, what I wrote above, is that you can, instead of thinking of a sequence as a list with a definite order, you can think of it mathematically as a function from the positive integers to a, where a is any set. So here we can express / describe this sequence as a function f from the set of positive integers to a, right? So we can describe this sequence as a function f from the set of positive integers to a, defined by, well, if you take f of any positive integer n, what is that going to give you? It's going to give you n squared. Okay, so f of 1 is 1 squared, f of 2 is 2 squared, f of 3 is 3 squared. So see, if I wanted to know what the 7th term was, I would plug in f of 7. 7 would be telling which term in the sequence I want, right? So f as a function from the set of positive integers to set a is saying, if I want to know the nth term of the sequence, well, f of n will tell me what the nth term of the sequence is. And so what is my doing? I'm associating to each positive integer n an element of a set A. And so a sequence can be thought of as a function where you map positive integers to elements of a set A. Okay, so f of 7 would be the 7th term of the sequence. 1, 2, 3, 4, 5, 6, 7. The 7th term is 49. And so if you plug in f of 7 into that equation, you get f of 7 equals 7 squared, which is 49. And so this equation defines this function f, and this function f is a mathematical description of that sequence. Okay, so you don't have to write out the infinite million terms of the sequence. You don't have to write the bracket notation for the sequence. You can just write this notate. You can write this function f as from z plus to a, defined by f of n equals n squared. And maybe say a is this set of real numbers or positive integers, because that's what we have here. But yeah, so if you define a function f appropriately, instead of having to express an infinite sequence, you can just describe a function that gives you that infinite sequence. Okay, so we're defining a sequence here as a function. Okay, from a set of positive integers to a. Okay, so notation. The sequence. So the sequence a sub 1, sequence a sub 1, a sub 2, a sub 3, a sub 4, and so forth, is also denoted, and I've been using it already, is also denoted by a sub n or as a sub n from n equals 1 to infinity. Okay, so I use the right notation just because I was just defining for you a sequence, and so I want to make clear what's going on. We're enumerating them from 1 to infinity, right? But this notation is a suggestive notation. In math, oops, what's going on? Gotta fix the, you might be able to see it. Okay. In math, sometimes we have what's called suggestive notation, meaning that instead of writing all the symbols with all the information you would need or the information that's there, instead we leave some notation out because that's standard, right? A sequence would, the standard way to express a sequence would be from n equals 1 to infinity. And so if you don't include that notation, the reader should know, okay, it's a sequence from n equals 1 to n equals infinity, because that's what you usually do, okay? If you do something weird, or if it's not clear from the problem or your solution what you're doing, if you're starting at n equals 4, then maybe you want to use the right notation, right? But a mathematician doesn't want to write more than he has to. If he can write less, he wants to write less. And so if I already know, if it's obvious you're going from 1 to infinity, a mathematician wants to not write that in. So the left one is often used, the left one is used much more than the right one, because it's not a matter of being lazy. You can get things done faster if you don't have to write as much, okay? Okay, so the left one is the more standard notation. Okay. So examples of sequences. Okay, so part A. So for part A, you have, let's say, the sequence defined by n over n plus 1. Okay, and that goes from n equals 1 to infinity. Okay, but then you have the term a sub. So this notation saying the set, this n over n plus 1 from n equals infinity, this is saying that a sub n is equal to n divided by n plus 1, right? Because that's what's inside the bracket there. So the notation where the a sub n is inside, it doesn't mean you might, instead of writing a sub n, you might write a sub n what it is, right? If a sub n is equal to n over n plus 1, this notation would really mean writing n over n plus 1 in the brackets, okay? So here I'm saying a sub n is n over n plus 1. And the sequence that's describing, that notation is describing, is the set where the first term you plug in 1, so you get 1/2, right? 1 over 1 plus 1 is 1/2. Then when n is 2, the start goes n equals 1, n equals 2, 2 over 3. And the next term is 3 over 4. The next term is 4 over 5, and so forth. Okay, so here I'm using the bracket notation to write the list, and then here I'm using the new notation that I just described. Okay, so that's an example of a sequence. Okay, another example of a sequence using the notation that's better to use is this one, negative 1 to the n times n plus 1 divided by 3 to the n. So now I'm just going to write it like that. So I'm not going to add n equals 1 to infinity over here, because the fact that I didn't write anything for the indices means that you're going to use the standard indices 1 to infinity for n. Okay, and so now a sub n is then what's inside the bracket. It's this expression. It's the thing that's highlighted there. So that's a sub n, right? That's a sub n. And the list it's describing is you plug in the value. So for n equals 1, you get negative 1 times 2 over 3. So you get negative 2/3. That's the first term. When n equals 2, you get negative 1 squared, which is 1. 2 plus 1 is 3. 3 over 3 squared is 3/9. It's 3/9. So I'm not going to simplify it. I'm going to write it as 3/9 because it corresponds with the numerator and denominator in that expression. And then for n equals 3, you have negative 1 cubed, which is negative 1, times 3 plus 1, which is 4. 4 over 3 cubed, that's 4 over 27. This is negative 4 over 27. Okay, and then the list continues. And then when you get to the nth term, you just have that expression there. Okay, and then comma, dot, 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 because it's an infinite sequence. And so when you describe the nth term of the sequence as an expression, you then have a next term anyway and a term after that. And so you just put comma, dot, 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 because you can't actually write infinitely many terms of a list ever. Okay. And so part C is a third example of a sequence. And this is the square root of n minus 3. Okay. But when you do the square root of something, you have to consider the fact that it can't be 0, right? And so we can't start the sequence at n equals 1 because you'd have a square root of a negative number, okay, for real numbers. And so this is from n equals 3 to infinity. Okay, so now we're starting to sequence at n equals 3 because we have to, because we're dealing with real numbers. And so now I need to use the other notation, the right one, in order to say where I'm starting. I can't start n equals 1, which means maybe it's not obvious what it is, or maybe it is because you'd start at 3, right? But a sub n is equal to the square root of n minus 3. Okay. And then this is again for n greater or equal to 3. Okay. So keep in mind that when I define a sub n now, I'm including n greater or equal to 3, right? Because I'm thinking of the term starting at the third time. It's not starting at the first. Before I just wrote a sub n equals this, because without, again, there's some suggestive notation here, right? I'm starting at n equals 1, right? So here I can't start n equals 1, which is the obvious choice, the normal choice. And so I'm including here n greater or equal to 3. Okay. And so then the sequence this is representing was when n equals 3, you have the square root of 0, which is 0. When n equals 4, the square root of 4 minus 3 is the square root of 1, which is 1. When you choose 5, you have the square root of 5 minus 3, which is the square root of 2. The next term is the square root of 6 minus 3, square root of 3. Okay, and so now you have that sequence there. Okay, so these are 3 examples of sequences and notations for how to express them. Okay, so now let's do an example. So an example, find a formula for the general term a sub n of the sequence. Okay, so solution. So the solution is to tell you what the sequence is. Okay, so here's the sequence: 3/5, comma, negative 4/25, comma, 5 over 125, comma, negative 6 over 625, comma, 7 over 3/125, comma, dot, dot, dot. Okay, so that's our sequence. Okay, and then this is also assuming the pattern of the first few terms continues. Okay, so solution. So let's see what we're given. Okay, so let's look at the terms given to us to find a pattern to determine what the future terms should be. Okay. Okay, so let's do that. I'm going to move this example to the next page. Okay. Okay, So a sub 1, right, is equal to 3/5. A sub 2 is equal to -4/25. A sub 3 is equal to 5/125. Okay. A sub 4 is equal to -6 divided by 625. A sub 5 is equal to 7 divided by 3/125. Okay, and then, okay, so these are the terms we have. So notice what's happening in the numerator. In the numerator, we're just adding 1, ignoring the negative sign. Ignoring the negative sign, what's happening in the numerator is that we're just adding 1 each time, right? When the first term is 3, the second term is 4, third term numerator is 5, the fourth term numerator is 6, right? So n is the index. And so if we want to express a sub n, right? If we want to express a sub n, well, the numerator is always 2 more than the index. As the index increases by 1, the numerator also increases by 1. And so that relationship stays. And so the numerator is n plus 2, right? The numerator is always 2 more than the index, n. Now for the denominator, the first denominator is 5, the second denominator is 25, the third denominator is 125, the fourth denominator is 625, and the fifth one is 3,125. The large terms you might not notice, but you might be able to tell quickly that these are powers of 5, right? 5 is 5 to the first, 25 is 5 squared, 125 is 5 cubed, 625 is 5 to the fourth, and 3,125 is 5 to the fifth. And so the nth term has as its denominator 5 to the nth power. Okay, so the denominator is 5 to the nth power, 5 to the first, 5 squared, 5 cubed, 5 to the fourth, 5 to the fifth. And so we're almost done. We have the numerator and denominator, but we don't have the sign. Well, notice that the odd terms, the first term, the third term, the fifth term, are positive. And the even terms, the second term, the fourth term, and so forth, are negative. And so what we want is something that will give us +1 for an odd n and a -1 for an even n. So just do -1 raised to the n plus 1 power. Okay, -1 is the n plus 1 power. When n is odd, n plus 1 is even, and -1 to an even power is +1. When n is even, n plus 1 is odd, -1 to an odd is -1. Okay, so you just need to add 1 to the exponent, because if you just did -1 to the n, even would be positive and odd would be negative. Since we want to flip it, we just add 1 to the exponent of -1 and we get the opposite. Okay, so a sub n is equal to -1 to the n plus first power times n plus 2 over 5 to the n. That is an expression, that is a formula for the general term a sub n of the sequence. So conclusion, so we find a general expression as this. We find a general expression a sub n is equal to that. Okay, so that's the solution to that example. Okay, so now let's do another example. And so this example is looking at the Fibonacci sequence. So the Fibonacci sequence, f sub n is defined recursively by the conditions f sub 1 is equal to 1, f sub 2 is equal to 1, f sub 3 is equal to 2. F sub 2 is equal to 1, f sub n is equal to f sub n minus 1 plus f sub n minus 2 for all n greater or equal to, for all n greater or equal to 3. Okay, so what I just said is that the Fibonacci sequence f sub n is defined recursively by these conditions. What these conditions are saying is that the first element of the sequence, the Fibonacci sequence, is 1. The second element is also 1. And then, starting with the third term, for n greater than equal to 3, starting with the third term, the nth term is the sum of the two previous terms. So f sub n, the nth term, is the n minus 1th term plus the n minus 2th term. So the first term is 1, the second term is 1, and then starting at 3, the nth term is the sum of the two previous terms. Okay, and so that's how you can define the Fibonacci sequence. This definition is defining the Fibonacci sequence recursively. Recursively means when you define something, instead of defining something with an explicit formula saying the nth term is this, or the nth term is n squared, instead of defining each term individually, you're defining the terms by the values of the sequence on previous terms. So your sequence is being built from previous terms. That's what defining a sequence recursively means. And so the Fibonacci sequence is defined here recursively, meaning that you're getting the next term of the sequence from the values of its two previous terms. Okay? And in order to do that, you need the values of the first two terms, right? In order to build the third term as the sum of the two previous terms, you need to be given the first and second term. And so here I give it to you. First term is 1, and the second term is 1. Okay, so each term, starting with the third term, is the sum of the two previous ones. So the first few terms of the Fibonacci sequence are, and so you have this sequence here. You have the first term is 1, second term is 1. The next term is the sum of the two previous ones, which is 2. The next one is 1 plus 2, which is 3. The next one is 2 plus 3, which is 5. The next one is 3 plus 5, which is 8. The next one is 5 plus 8, which is 13. The next one is 8 plus 13, which is 21. 13 plus 21 is 34, and so forth. Okay, so those are the first few terms of the Fibonacci sequence. Okay, so that's an example of a sequence. Okay, that's an important one in science and specifically biology. Definition. Definition 1. A sequence, A sub n, sequence A sub n has a limit, capital L, and we write the limit as n approaches infinity of A sub n equals capital L. Okay, we can move this here. And so we write this for, oh, let me quickly plug in my battery. It's running out of charge. Okay, I'm back. Okay, I have to charge it during the class. Okay, so you have the limit of A sub n equals L, or A sub n approaches L as n approaches infinity. Okay, so these are two notations for saying a sequence A sub n has the limit L. Okay, So definition: a sequence A sub n has limit L, and we write this or this. If we can make the terms A sub n as close to L as we like by taking n sufficiently large. Okay, so that's the definition of a limit of the sequence, of the limit of a sequence. So I'm going to write this. Okay, so below is the definition of a limit of a sequence. A limit capital L of a sequence A sub n. Okay. Okay, so we define a sequence, the limit L of a sequence A sub n. Okay, so a sequence A sub n has a limit L if we can make the terms A sub n as close to L as we like by taking n sufficiently large. Okay. Note if the limit of A sub n exists, we say the sequence converges. Or is convergent. Otherwise, we say the sequence diverges or is divergent. Okay. And so actually, I want to separate this, but I guess I'm going to include as part of the definition. So I'm going to write it like that. Okay. So this is definition 1. A sequence A sub n has the limit L. We use this notation. If we can make the terms A sub n in the sequence as close to L as we like by taking n, the index of the sequence, sufficiently large. If the limit of A sub n as n approaches infinity exists, we say the sequence converges or is convergent. Otherwise, if the limit does not exist, we say the sequence diverges or is divergent. Okay, so that's definition 1. So let me do definition 2. But before I do definition 2, I'm just going to give an example. So example is this. The sequence 1 over n from n equals 1. I'm just going to write the notation that adds more just so it's clear. So this sequence has 0 as a limit. Okay. And so this sequence has 0 as a limit. So if you look at the terms of this sequence, the terms when n is 1, you have 1 over 1. When n is 2, you have 1 over 2. When n is 3, you have 1 over 3. When n is 4, you have 1 over 4. When n is 5, you have 1 over 5, 1 over 6, 1 over 7, 1 over 8, dot, dot, dot. Right? So this sequence has 0 as a limit because we can get as close to 0 as we want by taking terms in the sequence sufficiently far out. Okay. We take terms in the sequence sufficiently large. Let me just use the same word large there. Okay. And so what do I mean by that? Well, what that means is that the terms, so consider the number 1 million. 1 millionth. Okay, so consider the number 1 millionth. Okay, the idea of saying that a limit of the sequence is 0 is that if I can take any number I want, and the terms of the sequence will be at most that far away from the limit as long as I take a term far enough out into the sequence. So for instance, consider the number 1/1,000,000. If you consider all of the terms after the millionth term is less than 1/1,000,000th away from 0, right? The terms are 1/n. And so it's 1/1, 1/2, 1/3, 1/4. And so no matter how small of a number I choose, all the terms of the sequence will be less than that distance away from 0, as long as I consider only terms of the sequence large enough, far enough out into the sequence. So even a number like 1/1,000,000th, which is really small, all of the terms of the sequence after the millionth term are less than a millionth away from 0, right? Because the millionth term is 1/1,000,000. The next term is 1/1,000,001. The next term is 1/1,000,002. The next term is 1/1,000,003. And so all those fractions will have a denominator larger than a million, which means 1 over a number larger than a million is less than a millionth. And so all the terms after the millionth term is less than a millionth away from 0. And so similarly, you can choose any number you want. It doesn't have to be powers of 10 in the denominator. You could choose 1/3,487,000, 1/7,587,081,005, right? Any number you want, no matter how small it is, all you have to do is go far enough out into the sequence, and all the terms after that term will be less than that away from 0. And so that's the meaning of saying 0 is a limit of that sequence. Okay? So this sequence has 0 as a limit. And so what I'm illustrating here is how, in this example, what it means for 0 to be the limit, a limit of that sequence. Okay? And how you can kind of visualize what a limit of a sequence is. Okay? So definition 1 is the easy definition of a limit. Okay? Now, you might ask, why do I want a more difficult definition of something? Why not use the easy one? Definition 1 is not really defining it. Definition 1 is like, definition 1 is putting the definition of a limit in layman's terms. It's putting it in a way that kind of makes sense to people, but it's not really defining it. Okay, so what we said is that a sequence A sub n has a limit L if we could make the terms A sub n as close to L as we like by taking n sufficiently large, right? I mean, that can be difficult to understand, but it's, in some ways, it's closer to English, but it's not really defining it. And so now definition 2, I'm going to go into more mathematical language to give a precise mathematical definition of what a limit is. So this is definition 2. A sequence A sub n has a limit, capital L, and we write the limit as n approaches infinity of A sub n a sequence A sub n has limit L, we write limit A sub n equals L, or A sub n approaches L as n approaches infinity, if we can make the terms, sorry. A sequence A sub n has limit L, and we write A sub n, limit A sub n equals L, if, here we go, if for every epsilon greater than 0, there is a corresponding integer, capital N, such that if little n is greater than capital N, then the absolute value of A sub n minus L is strictly less than epsilon. Okay, So definition 2, a sequence A sub
Professor?
n. Yeah,
What is epsilon again?
it's a real number.
So epsilon is any real number.
No, well, hold on. It's sort of epsilon represents a real number. Now, in the definition, I'm talking about epsilon as a real number in a certain way, right? So to ask me what epsilon is, it's a real number. That's a different question than saying what is happening with epsilon. What is the role of epsilon in the definition? Does that make sense? Okay, so I think what you mean by your question is what role does epsilon play in the definition? Epsilon is a real number, and the definition is saying a sequence A sub n has the limit L with that notation if for every real number epsilon greater than 0, there is a corresponding integer capital N such that if little n is greater than capital N, then the absolute value of A sub n minus L is less than epsilon. So I realize it's difficult to understand. Give me a little bit of time, and then I'm going to try to make that clear for you. Okay, so so in order to explain this, make sure you maybe wrote this down, right? Because I'm going to go to the whiteboard in a second. Okay, make sure you have written this down. Okay, a sequence A sub n has the limit L, and we write the limit is A sub limit A sub n approaches limit is n approaches phi of A sub n equals L, or A sub n approaches L as n approaches infinity. I'm just moving. If for every epsilon positive, there is a corresponding integer capital N, such that if little n is greater than capital N, then the absolute value of A sub n minus L is less than epsilon. Note, epsilon represents a real number. Okay, it represents a real number, but remember, epsilon is positive, is assumed to be positive in the definition, right? So I'm answering the question what epsilon is. It's a real number, but don't mistake that for thinking it's any real number. The definition is saying it's assuming it's a positive real number. Okay. Okay, so that's the definition. And then that was the other problem. Okay, so now I'm explaining the definition of a limit. So here's the real line, right? This is 0. Let's say this is the value, the real number, capital L. It's just an element of the real line. It's a real number, okay? Let's say A sub 1 is this real number, which is closer to, it's positive, but it's closer to 0. Let's say A sub 2 is this real number. Let's say A sub 3 is this one, okay? Then let's say A sub 4 is this one. And then let's say A sub 5 is this one. Okay, and then A sub 6 is this one. Okay, A sub 7 is this one. A sub 8 is this one. A sub 9 is this one. That's an A. Okay, A sub 8, A sub 9. And so you see that first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. And so it looks like these terms are getting closer and closer to L, right? Kind of. So now let's look at this interval around L. Okay, this open interval around L. And then let's look at, let's say we have, so the left endpoint of the open interval is L minus epsilon, and the right endpoint is L plus epsilon. Okay, so this, the real number here at this side is L minus epsilon. This is L plus epsilon. So really you have this radius here is little epsilon. Okay, this distance between this black dot and this blue thing, this is epsilon, positive epsilon, and then you have to go this distance epsilon, positive epsilon to get to there, right? It's negative. You're going to the left, but if you were thinking of how far you would walk, right, it would be epsilon. Okay. Now, so you have the point L, and it's the center of this small epsilon length radius ball in R. Now let me also label this term a sub capital N plus 1. And this dot here is a sub capital N plus 2. Okay, that's this point, and this is this point. Okay, and L is the limit. So what the limit definition is saying is that capital L is the limit of your sequence, right? Let me label it as a red. Okay. Red L, that's the limit. It's this real number here, right? L is a limit of your sequence. If for any positive real number epsilon, let's say it's the epsilon I put in the picture here. For any positive epsilon you choose, eventually all the terms in the sequence are inside of that blue area. Eventually all the terms of your sequence are less than epsilon away from capital L. Okay, that's the idea of a limit. So let's say I choose epsilon equals 1. Then the definition of the limit says, well, if I say the limit is 5 of your sequence, then I can choose any real number I want. Let's choose epsilon equals 1. If the limit is 5, then eventually all the terms of the sequence will be within 1 of the real number 5. Keeping the limit being 5, instead of 1, let's choose 1 million. Okay, so if the limit of your sequence is 5, then according to the definition of limit, what you're saying is that if I chose a real number like 1 millionth for epsilon, if I made the radius, if I made this distance from the red dot to either endpoint 1 millionth instead of 1, eventually all the terms of the sequence will be, all of them eventually will be within a millionth of that point L. And instead of a millionth, if I choose 10 trillion, if instead of epsilon was 1 trillion, 1 10 trillion, eventually all the terms of your sequence will be within 1 10 trillionth of L. So that's the idea of a limit of a sequence. It's a real number such that eventually, no matter how small of a distance you choose, all the terms will be as close as you want to the limit, to that limit. Okay? Now, if you choose a smaller value for epsilon, you'll have to probably go further out into the sequence. So if I chose 1 as epsilon, saying eventually all the terms are within 1 of L means maybe I only need to look at after the 5th term, right? Maybe all the terms after the 5th one will be within 1 of L. But instead of 1, if I chose a millionth, if I said, well, you know, eventually all the terms will be within a millionth of L, then what I mean is that there's some term, capital N, such that all the terms after the capital Nth term will be within 1 millionth. That capital N will probably have to be larger if you're thinking of a millionth instead of 1, right? Saying eventually all the terms are sufficiently close to your limit means that for each different epsilon you choose, you'll need a different probably corresponding capital N to say all the terms after the capital N term are within that new epsilon of your limit. So if you want to get within 1 of the limit, maybe you need all the terms after the 5th term. If you want within a millionth of the limit, maybe you need after the 100th term, right? But there's some term, right? Saying the limit is L means there's some term of the sequence such that after that term, all the terms are within epsilon of your limit. Okay? That's what the limit of a sequence is. All right? So for each epsilon you choose, there's a corresponding value capital N such that all the terms after the capital Nth term will be within epsilon of your limit. Okay, that's what this definition is saying here. Okay, definition 2. A sequence A sub n has a limit capital N if as a limit capital L if for every epsilon, every positive epsilon we choose, there is a corresponding integer capital N, such that if little n is greater than capital N, then the absolute value of A sub n minus L is less than epsilon. In more English terms, no matter what epsilon, positive epsilon value you choose, there is some value of integer capital N, such that after the capital Nth term, right? Little n is the term after the capital Nth term. Every term after the capital Nth term will be less than epsilon away from your limit capital L. The absolute value of A sub n minus L is the distance from A sub n and L, right? The absolute value of 1 minus 3 is 2, because the distance between 1 and 3 is 2, right? The distance doesn't matter which one's larger. So the absolute value of 1 minus 3 equals the absolute value of 3 minus 1, right? The distance between 1 and 3 is 2, right? It doesn't matter the order. So what this is saying is that no matter what epsilon, positive epsilon you choose, there is a corresponding integer, there's a corresponding term, capital N, of your sequence, such that after the capital Nth term, all the terms after it are less than epsilon away from that limit L. Okay? That's what definition 2 is saying. Okay. That's the definition. And so let me continue. Okay, so theorem. If the limit as x approaches infinity of f of x is equal to L, and f of n is equal to a sub n, when n is an integer, okay, but I'm going to write when n is an instead of integers. So when n is in the set of integers, then the limit as n approaches infinity of a sub n is equal to L. Okay, so the limit as x approaches infinity of f of x equals L, and f of n is equal to a sub n when n is an integer. Okay, so write that when n is an integer. Then the limit of a sub n is equal to L. Okay. So what does that mean? Let me illustrate that. What that theorem is saying is that if here's the y-axis, here's the x-axis, and you get you have the origin there. You have 1, 2, 3, 4. Okay, and then so let's say you have let's say you have this graph here that looks like this. Okay, where your function, the graph of your function, right, has y equals L as a horizontal asymptote, right? Then if you think of the function f, right, so f of n is equal to a sub n. So for instance, here's the value at 1, here's the value at 2, here's the value at 3, here's the value at 4. So this height is a sub 1, this height is a sub 2, this height is a sub 3. The height of that point is a sub 4, right? So a sub n is telling you the a sub n is the height of the function f at n equals 1, n equals 2, n equals 3, n equals 4, right? And this is the graph of y equals f of x. Okay, and so what it's saying is if the limit as x approaches infinity of f of x is L, which is happening here, because it has this horizontal asymptote, right? This is telling you the limit. This tells you that the limit as x approaches infinity of f of x is equal to L, right? So if that happens and f of n is defined like this equals a sub n, then the conclusion is that the limit of a sub n equals L. The conclusion of that theorem is that the limit as n approaches infinity of a sub n also equals L. And so if you're taking terms of the sequence as being heights of this function, then since the graph is approaching the height L as x approaches infinity, a sub n is also going to approach L as n approaches infinity. Okay, that's the theorem I just wrote down on Word. And so when you see the picture, it makes complete sense, right? Okay, so another definition. the limit, okay, so I'll stop soon. The limit as n approaches infinity of a sub n is equal to infinity means that for every epsilon positive, for every positive number capital M, there is a positive integer capital N such that if little n is greater than capital N, then a sub n is greater than capital M. Okay. Okay, so definition. Limit as n approaches infinity of a sub n equals infinity means that for every positive number capital M, there's a positive integer capital N, such that if little n is greater than capital N, then a sub little n is greater than capital M. That means that saying that the limit of your sequence is infinity means that for any value of capital M you choose, positive, eventually all the terms of your sequence will be of height larger than that capital M. Okay? So no matter how large of a capital M you choose, no matter how high of a height you choose, the sequence approaching the limit of the sequence being infinity means eventually all the terms of your sequence will be higher than that, right? It's like if you're doing in the Olympics, if you're jumping over that thing and they keep putting it higher and higher, you have to try to jump over it, right? This is a sequence where no matter how high up you have to go, the sequence will go up. It won't fall, it'll stay up, okay? And so that's how a sequence approaches infinity. Eventually, all the terms of the sequence get larger and larger, okay? But it doesn't have to keep getting larger. It can go up and down. It's just that no matter how high of a height you choose, no matter what positive number M you choose, there is a corresponding positive integer capital N, such that all the terms after the capital Nth term will have value larger than that capital M. Okay? Let me keep going with the definition. If the limit as n approaches infinity of a sub n is infinity, then the sequence a sub n is divergent to infinity. Okay, so a sequence is divergent to infinity if the limit is infinity. Okay, and so next time we will talk more about limits, and I'll talk about laws about these limits. Okay, so this is the end of class. I'm going to quickly just assign a homework assignment, and then we are done. Okay, so next time we will continue with 8.1. Also, homework. So for next class, I want you to do homework 17. Okay, so homework 17 is due next class, and it's on sections 7.4 and 7.7. Okay, so that homework will be due next class. It's homework 17. Okay, and so work on that, and then that homework will cover all the remaining homework questions for test 2, right? And also a reminder, test 2 is on April 26th at the start of class, right? At the start of class. Okay, at 1:40 p.m. Okay, And you use the same link to go to the exam, same link to attend the exam, to take the exam, as the link to go to class every week, okay? So the same link you're using to go to class, this class, and every other class, use that same link on April 26th to just attend class normally, and that will be where the exam is, okay? So the homework is due next class. The exam, test 2 is on April 26th, and I'll see you on Wednesday. Bye.
Professor.
Yeah?
How many questions will be on the exam?
Sorry?
How many questions will be on the exam?
What's your question?
How many questions on the exam?
Oh, how many questions? So I'm not going to say, right? So it's an hour exam. I mean, yeah, it'll be an hour exam. Okay. So it's an hour exam. The review sheet is online. So if you go to tests and then you go to test 2, there's a review sheet there. They'll help you review. The exam will be an hour. It'll be structured very similar to the first exam. So I don't think there'll be any, won't be any problem. You'll have plenty of time to take the exam. Okay. So I'll see everyone on Wednesday. Bye.
Have a nice day, Professor.
You too. Bye.